Welcome students to this section of MCQs. So let us see the first MCQ for this section. Glycogenolysis in muscle is increased when glucagon levels are high, epinephrine levels are low, insulin levels are high during strenuous exercise in the well-fed state. So your option should have been, if you have chosen D, then you have done a good job. Now why can't it be the A? When glucagon levels are high, does glycogenolysis take place? Yes, glucagon is responsible for breaking down glycogen. But look at the question. It says glycogenolysis in muscle. In muscle, glucagon doesn't have any action. It is mainly on the liver that the glucagon acts. The second question, epinephrine levels are low. When epinephrine levels are high, it will stimulate glycogenolysis in muscle. Insulin levels are high. Insulin levels are high in the well-fed state, and in the well-fed state, glycogen is going to be synthesized. So glycogenolysis will not occur. During strenuous exercise, yes, glycogenolysis has to occur to provide glucose 6-phosphate, which will enter into glycolysis and give energy to the muscle. In the well-fed state, again the same, insulin levels are high, so glycogen has to be synthesized. Glycogenesis will be taking place. So let us go to the next question. The glycogen storage disease characterized by exercise intolerance is von Gerg's, Cory's disease, Anderson's, McArdle's, Torrey's. So exercise intolerance is present in which glycogen storage disorder? McArdle's. What is happening here? How do you remember all this? Von Gerg's, please remember, it is always glucose 6-phosphatase. Cory's is debranching enzyme. Because some people remember it as CD. Cory's is for debranching enzyme. Then Anderson's is for branching enzyme. This will be debranching. CD, AB. A is for Anderson. It causes branching enzyme. McArdle is for muscle. Muscle, what is happening? In muscle, phosphorylase is affected. It is McArdle's. So when muscle phosphorylase is affected, muscle phosphorylase is not there, glycogen phosphorylase, what will happen? The muscle glycogenolysis will not take place, and this will lead to exercise intolerance most of the time, because during exercise the muscle requires glycogenolysis. That is when it doesn't take place, it will lead to exercise intolerance. This is how people remember it. Muscles, HERS is the next one. When you have muscle phosphorylase, HERS will be liver phosphorylase. HERS will be liver phosphorylase. Torrey's is also there. Cory's, what all are there? Von Gerg's is glucose 6-phosphatase. Cory's is debranching enzyme. Anderson's is branching enzyme. McArdle's is muscle phosphorylase, and Torrey's is because of the next enzyme, muscle phosphofructokinase, PFK, muscle phosphofructokinase. So let us look at it further. The next question. A child was brought with complaint of swelling in the abdomen and history of reeling sensation. On examination, the liver was found to be enlarged. Lab results showed increased serum uric acid and hypoglycemia. There was no increase in blood glucose even after IV glucagon administration. The enzyme deficient in this case is. So a case history has been given. Case history means you will have to read it out properly. So what was your answer? The answer is glucose 6-phosphatase. What is this glucose 6-phosphatase? It is von Gerg's disease. Now why do you think it is von Gerg's? One, there is swelling in the abdomen, and this may be because of hepatomegaly. Hepatomegaly is seen in all the glycogen storage disorders. Now von Gerg's is also very special in the sense it increases uric acid compared to other glycogen storage disorders. Why does von Gerg's increase uric acid? Because glucose 6-phosphate will accumulate, and this glucose 6-phosphate gets diverted to HMP shunt, and it will lead to more production of ribose 5-phosphate, which will lead to more production of purines. Purines, more production gets more degraded, and that will lead to increased uric acid. and plus there is hypoglycemia. Why there is hypoglycemia? Because gluconeogenesis, one of the enzymes, key enzyme is glucose 6-phosphatase. So when that is not taking place, glucose 6-phosphatase is not converted to glucose. So it will lead to hypoglycemia. The key word here was there was no increase in blood glucose even after IV administration of glucagon. So when glucagon is there, it mainly acts on hepatic glycogenolysis to bring about glucose release. So when that is not happening, it will lead to decreased hypoglycemia, and also it will lead to especially early fasting hypoglycemia is seen in glucose 6-phosphatase deficiency, von Gerks. Let us go to the next question. All the following are true regarding the enzyme glucose 6-phosphatase, except it is the key enzyme of gluconeogenesis. It is present in endoplasmic reticulum of hepatocytes. It is deficient in von Gerks. It belongs to class 3 hydrolases. Its activity is increased by insulin. What was your answer? You should have been able to answer. The answer is insulin. Its activity is increased by insulin. No, its activity is going to be decreased by insulin. Why? This enzyme is a key enzyme not only for gluconeogenesis but also for glycogenolysis. So when that happens, they both are meant to increase the blood glucose level. So whenever insulin levels are high, we don't want to increase the blood glucose levels again, because it is already because of high blood glucose level. So in such cases, this enzyme cannot act. The rest all of it are true. It is a key enzyme of gluconeogenesis and also glycogenolysis. It is present in the endoplasmic reticulum of the hepatocyte. You might be wondering, it should have been present in the cytoplasm. You have all read that gluconeogenesis takes place in the cytoplasm, except for this enzyme, glucose 6-phosphatase, which is present in the endoplasmic reticulum. It is deficient in von Gerks. It belongs to class 3 hydrolases. Were you confused with this? You might have been, because we are talking of an enzyme and to which class it is belonging to. Remember, enzymes have been classified into oxylyl, oxidoreductases, transferases, hydrolases, etc. So this is a phosphatase. Phosphatase means it uses water, releases the inorganic phosphate. So it belongs to the class 3 hydrolases, uses water to break a bond. So the correct answer is its activity is decreased by insulin, would be the true statement. This is the wrong answer. So let us look at this is wrong. It is not the wrong answer, it is the right answer, but what I mean to all are true, this is false. So let us go to the next question. All the following are fates of pyruvate except converted to acetyl-CoA, used for gluconeogenesis, converted to aspartate, used for the formation of oxaloacetate, converted to lactate. What do you think? Which answer did you get? Converted to aspartate. Now why this is wrong, or why this is not a fate of pyruvate? Pyruvate to acetyl-CoA is by pyruvate dehydrogenase complex. Gluconeogenesis, yes, it is an important substrate for gluconeogenesis. Converted to aspartate, no, it is actually pyruvate alanine transaminase converts pyruvate to alanine, not to aspartate. Used for the formation of oxaloacetate, yes, pyruvate carboxylase converts pyruvate to oxaloacetate. Converted to lactate, yes, lactate dehydrogenase converts pyruvate to lactate. So converted to alanine could have been the right answer, right statement here, but this was the only false statement. So let us go to the next question. Glucose 6-phosphate can enter the following pathways except glycolysis, HMP shunt, polyol pathway, uronic acid pathway, glycogenesis. What was your answer? The answer should have been polyol pathway. Why? Glycolysis, yes, glucose 6-phosphate is further converted to fructose 6-phosphate, so it enters glycolysis. HMP shunt, yes, glucose 6-phosphate dehydrogenase. Polyol pathway is for glucose itself. Remember, polyol pathway results in the formation of sorbitol. Glucose is converted to sorbitol. Fructose is converted to sorbitol. So it is the polyol pathway where one more alcohol group gets added to glucose to form sorbitol. This is important in diabetes mellitus where the glucose levels keep on increasing. They all get converted to sorbitol, and it is the accumulation of sorbitol which brings about most of the effects of diabetes mellitus. The complications of diabetes mellitus are because of the conversion of glucose to sorbitol. Uronic acid pathway, yes, glucose 6-phosphate has to form glucuronic acid. That is the uronic acid pathway. Glycogenesis, yes, it has to form UDP glucose. Only then it can give that glucose to another molecule and result in the formation of glycogen. Let's go to the next question. AcetylCoA acts as a substrate for all the enzymes except citrate synthase, thiolase, acetylglutamate synthetase, glutaminase, AcetylCoA carboxylase. So your answer would have been glutaminase. Now, where is it acting? Let us see. Citrate synthase, yes, acetyl-CoA plus oxaloacetate to form citrate, the first reaction of TCA cycle. Thiolase, we are talking of the reversal of beta oxidation, or even in ketone bodies, thiolase is used for the further action of acetyl-CoA. Acetylglutamate synthetase, yes, to form N-acetylglutamate, which is required for urea formation, which acts as a allosteric effector for carbamyl phosphate synthetase 1 in urea cycle. Glutaminase is not involved. Acetyl-CoA carboxylase, yes, de novo synthesis of fatty acids, acetyl-CoA to malonyl-CoA. So acetyl-CoA acts as a substrate for all these except glutaminase. Glutaminase converts glutamin to glutamate. Let's go to the next question. All the following enzymes are involved in anaplerotic reactions of the citric acid cycle except pyruvate carboxylase, aspartate transaminase, glutamate dehydrogenase, malic enzyme, ATP citrate lyase. So which of these is not an anaplerotic reaction of the citric acid cycle? ATP citrate lyase. Why is pyruvate carboxylase an anaplerotic? Pyruvate is converted to oxaloacetate, an intermediate required, the first compound required in the TCA cycle, citric acid cycle. Aspartate transaminase converts aspartate to oxaloacetate. Glutamate dehydrogenase converts glutamate to alpha ketoglutarate. Malic enzyme converts malate to pyruvate, whereas ATP citrate lyase is a cytosolic enzyme which uses ATP to lyase citrate to release acetyl-CoA and oxaloacetate. But remember, ATP citrate lyase is happening in the cytosol and not in the mitochondria, and we needed replenishment for anaplerotic are the filling up reactions which fill up the used up substrates. So the filling up of this will not take place in anaplerotic reactions. So ATP citrate lyase is the right answer. So let us look at the next question. Which vitamin is involved in the HMP shunt? B1, B2, K, E, C. Which did you write? Which did you think? Vitamin B1. Which enzyme? Transketolase. Remember, the RBC transketolase levels are used to determine whether a person is deficiency in thiamine or not. Vitamin B1 is thiamine, and thiamine pyrophosphate acts as a coenzyme in the HMP shunt. So it is further reactions of the different transketolase. It acts as a coenzyme. Vitamin B2 is not involved. It is alpha ketoglutarate dehydrogenase, TCA cycle, pyruvate dehydrogenase, succinate dehydrogenase, there where it is involved, not in the HMP shunt. K is coagulation, vitamin E is antioxidant, vitamin C is also an antioxidant. Let's go to the next question. All of the following statements regarding NADPH are true except it is used by the enzyme glutathione reductase. It is used for the de novo synthesis of fatty acids. It is used for the de novo synthesis of cholesterol. It produces 3 ATPs via oxidative phosphorylation. It is produced in the HMP shunt. So this is an easy one, should have been an easy one. NADPH never produces ATP. NADPH will not produce. It is involved in all other things but never produces ATP. It cannot enter the electron transport chain, and especially via it never produces ATP, and definitely not via oxidative phosphorylation, where it is only NADH and FADH2 which are entering the ETC. So it is used by the enzyme glutathione reductase. Yes, to convert glutathione, reduced glutathione to oxidized glutathione, GSSG to GSH. To convert this, it is glutathione reductase, and this is NADPH is required. So what do we mean by that? Oxidized glutathione is converted to reduced glutathione, and for this NADPH is required, and this comes from the enzyme that is it is required for NADPH, and the enzyme is glutathione reductase. It is used for de novo synthesis of fatty acid. Yes, all the reductive biosynthesis required, including fatty acids or cholesterol. It is produced in the HMP shunt. Yes, NADPH is most important byproduct of HMP shunt. Let's go to the next one. All of the following are true regarding HMP shunt except it provides NADPH. It helps in maintaining the integrity of RBC membrane. It provides pentosis for de novo synthesis of purine nucleotides. It provides energy to RBC. It provides reducing equivalents for the synthesis of cholesterol. So this should have been easy because of the last question. Yes. So it is except, so it does not provide energy to RBCs. RBCs get their energy only by anaerobic glycolysis. So does HMP shunt take place in the RBC? Yes, it takes place, but it is having entirely different function, and that is to provide NADPH. NADPH, again the same reaction, glutathione reductase, and this helps to maintain the integrity of the RBC membrane. It provides pentosis. Yes. It provides reducing equivalent for the synthesis of cholesterol. Yes. Let's go to the next question. All of the following statements regarding glucose transporters are true except GLUT1 is present in erythrocytes, GLUT2 is present in the serosal cells of the enterocytes, GLUT4 is present in skeletal muscle, GLUT5 transports fructose, GLUT2 is insulin sensitive. So what was your answer? Should have been able to answer it. GLUT2 is insulin sensitive. No, it is GLUT4 which is insulin sensitive, not glucose transporter 2. What about the other ones, other choices? GLUT1, is it present in erythrocytes? Yes, it is present in RBCs. GLUT2 is present in the serosal cells of the enterocyte. Yes, it is just a facilitated transport which is required for the absorption of glucose. GLUT4 in skeletal muscles. Yes, this is the one which is insulin sensitive and gets translocated to the plasma membrane upon stimuli. So it is present in skeletal muscle. 5 transports fructose. Yes, and GLUT2 is insulin sensitive. No, wrong. It is present in the liver and the pancreas. There it need not be sensitive to insulin. Let us continue with the remaining questions in the next session.